In our next skill, simplifying rational expressions, it's going to be very important to remember how to factor quadratic expressions. So we're going to start off by reviewing factoring quadratic expressions. When you have a trinomial with an x squared term, an x, and a regular number, you're going to factor it into two binomials. The first thing you always want to do for any factoring problem is check for a GCF, or greatest common factor. And in this first example, there is no GCF that I can factor out. So I go to two binomials. And I want my first two terms in the parentheses to multiply to the first term of the trinomial. So I need an x and an x to multiply to x squared. Then my other two numbers, my last two numbers, need to multiply to the last term of the trinomial. So I think of all the things that multiply to 12, and I've got a lot of options. There's 1 times 12, 2 times 6, 3 times 4, or it could be two negatives, negative 1 times negative 12, negative 2 times negative 6, negative 3 times negative 4. And I picked the pair that will add to the middle term, negative 8x. And so that would have to be two negatives, negative 2 and negative 6. So my middle terms multiply to negative 2x, my outside terms multiply to negative 6x, and negative 2x plus negative 6x adds up to negative 8x. So that's my answer, x minus 2 times x minus 6. And you can always check your answer by FOILing or using the distributive property. So if I multiply this out, I get x squared minus 6x minus 2x plus 12, combining my middle terms, x squared minus 8x plus 12, which is what I started with, so I know I did it right. In the next example, again, I check for a GCF, and I can't think of any factors that 6, 13, and 5 have in common other than 1. So I can't factor out a GCF. So I go to my two binomials, and my first two terms need to multiply to 6x squared. So I have a dilemma because it could be 6x and 1x, or it could be 2x and 3x. And I don't know which, so I just try one. So I'm going to guess 6x and 1x. And I need to be prepared to change that if this doesn't work. But I'll give it a try. Now for my last two terms, I need them to multiply to negative 5. So that has to be a 5 and a 1. I need to keep in mind that they will be opposite signs to multiply to negative 5, but I don't know where the negative, one's going to be negative, one's going to be positive. I don't know which, so I don't worry about my signs yet. But it's got to be a 5 and a 1. But I don't know if the 5 goes first and then the 1, or the 1 and then the 5, so I just try something. So I'm going to try the 1 first and the 5. And when I multiply my inside terms, I get 1x. My outside terms multiply to 30x. And then I check to see if those add up to the middle term in the trinomial. 1x and 30x do not add to 13x, even if one of them is negative, so that didn't work. So I erase the 1 and the 5, and I try switching them to see if that works. And we get a 5 here and 1 here. Now I have 5x for my inside terms, and 6x times 1 is 6x. 1 has to be negative. There's no way that's going to add up to 13x. So that didn't work either. And since neither of those worked, the 6x and the 1x must be wrong. So now I'm going to change those to be 2x and 3x. So this is the guess and check process. Sometimes you get lucky and you guess right in the beginning, and if you don't, oops, 6x and 3x. So that is the other thing that multiplies to 6x squared, 2x times 3x. Now, I already have a 5 in the first spot and a 1 in the second spot, so I'll try that and see if it works. And this gives us 15x and 2x. Now I want these to add to 13x, and one of them does have to be negative so that they multiply to negative 5. So if I make 2x negative, that will add to 13x, which means I need a negative sign in front of the 1. So 2x times negative 1 gives me negative 2x. And then if I put a plus sign in front of the 5, I get positive 15x, which does add these up to positive 13x. So now I finally got it right. 2x plus 5 times 3x minus 1. So we have to be patient and try all the different combinations until we get something that works. Now in the next example, first we always check for a GCF. For 4 and 49, nothing goes into both of those besides 1, so no GCF. But whenever you have two terms that are being subtracted and they're both perfect squares, we call this a difference of squares. And it always factors into two binomials that are the same, except they have opposite signs in the middle. So what we basically do is take the square root of both of these, and it factors into two binomials. The square root of 4x squared is 2x, so it's going to be 2x and 2x. And then the square root of 49, or what number times itself is 49, is 7. So these last terms are both going to be 7. Because I want two binomials that are the same, except one of these is going to have a plus in the middle, the other will have a minus. And that's going to be the answer. Now, the reason this works is our middle terms will multiply to positive 14x, our outside terms will multiply to negative 14x, and when we combine those together, we get 0, so there's no middle term, which is why our expression that we started with only had two terms, because the middle term is 0x. So whenever you have two perfect squares that are subtracted, you always want to factor it into two binomials that are the same, except one has a plus, one has a minus. And in the last example, again, we check for a GCF first. This time I do have a GCF, so I always start by factoring out my GCF. These have a 3 in common. They also have an x in common. So I can factor out 3x. So I write 3x in front of a set of parentheses. And I need to figure out 3x times what will give me 3x squared. That would be multiplied by another x. 3x times x gives me 3x squared. So it's kind of like the distributive property backwards. Then for the second term, I need to figure out 3x times what will give me negative 12x. Well, I want a negative, and 3x times 4 is 12x. So I get 3x times x minus 4. And after factoring out the GCF, I check and see if it can be factored more. In this case it can't. I can't do any more factoring, so I'm done. All I could do in that one was factor out a GCF.